All right, if you've ever built anything that talks over a network, you've probably bumped into the CAP theorem. It's one of those foundational ideas in distributed systems. But here's the thing, it's also one of the most misunderstood. So today, we're going to pull it apart, deconstruct what you think you know, and get to what it really means when you're building software.
First things first, we have to tackle the biggest misconception right off the bat. It's that famous, catchy phrase that we all learned, the pick-two myth. It's how most of us were introduced to CAB, but honestly, it's a pretty dangerous oversimplification.
You've seen this diagram, right? A nice, neat little triangle. On the corners, you have consistency, availability, and partition tolerance. And the story goes, you can have any two you want, but you can never have all three. It's a tidy little package. But is it actually true?
Well, not really. The truth is a whole lot more interesting. Because in any real-world distributed system, and by that I mean any system with more than one computer talking over a network, you don't actually get to pick. One of these three isn't a choice at all.
So, to really get our heads around the actual trade-off, we have to get super precise about what these words mean. You know, the casual, everyday definitions are what got us into this pick-two mess in the first place. So let's lock in the strict technical definitions. First up is consistency, and this is a big one. This isn't just about your data eventually looking the same across all your nodes. The formal proof of the theorem talks about something much stricter called linearization. What that means is your entire cluster of machines must act like one single perfect computer. If I write a value, the very next read, no matter which machine it hits, must see that new value, or get an error. No excuses.
Next up, availability. This one seems easy, but the fine print is absolutely crucial. All it means is that the system always gives you a response. That's it. It does not promise that the response has the latest data. So if a node gives you an answer, even if it's stale data from last week, it is technically available. The system is only unavailable if it gives you an error or just times out.
And here it is, the absolute key to the whole thing, partition tolerance. This isn't a choice you get to make, it's a fact of life. Networks are unreliable, packets get dropped, routers crash, someone trips over a cable. If your system is distributed, you will have network partitions. You can't just wish them away. So you don't get to sacrifice P, it's mandatory. This means the real choice is always between C and A, but only when a partition happens.
So how does this actually play out? The classic example that makes this all click is called the split brain problem. It's the perfect little scenario that shows exactly why you're forced into this corner the moment a network fails. Okay, imagine a super simple database with just two nodes, A and B. All of a sudden, the connection between them is cut. They're flying blind, totally unaware of each other. Then, a client connects to node A and makes a deposit, writing balance equals $100. A moment later, another client connects to node B and asks to read the balance. So, what does node B do now? This is the moment of truth. Node B has exactly two choices. It can choose consistency. It knows it can't talk to node A, so to avoid giving out potentially old data, it just returns an error. The system is consistent. No one gets wrong information. But it's not available. Or it can choose availability. It just responds with the last data it had, which might be balance equals 0. The user gets a response, everything seems fine, but the system just served incorrect data. You lost consistency. You see? At that exact moment, you cannot have both.
Okay, so that sounds pretty bleak, doesn't it? A hard choice between being correct or being online. But modern systems are a lot more sophisticated than that. They figured out some really clever ways to manage this trade-off, instead of just flipping a single switch between CP and AP.
The key to this is a concept called tunable consistency, and it's usually done with something called quorums. You can think of a quorum as basically a voting system for your data. Instead of demanding that all your nodes agree on something, you just need a certain minimum number to vote yes for a read or a write to be considered successful.
And it's all driven by this incredibly simple but really powerful little formula. R plus W is greater than N. So let's break down what that means. So N is just the total number of copies or replicas of your data that you have. W is the write quorum. That's how many nodes have to confirm a write before you tell the user, yep, it's saved. And R is the read quorum, the number of nodes you have to ask before you can return an answer to the user. The real magic happens when you start playing with these numbers.
This table shows it all. Let's say we have 3 replicas, so N equals 3. If you set your write quorum to 3 and your read quorum to 1, writes are going to be slow because they have to go to every node. But reads are super fast.
And because 3 plus 1 is 4, which is greater than n, your consistency is guaranteed. Now look at that bottom row. This is a really common setting for systems like Cassandra. W and R are both set to 1. Reads and writes are blazing fast. But 1 plus 1 is 2, which is not greater than 3. You no longer have guaranteed consistency. You've explicitly tuned the system for high availability and performance, accepting what's called eventual consistency.
This brings us to the next level of thinking about all this. The CAP theorem is brilliant, but it's got one huge limitation. And that limitation led to the development of a more complete framework called PASL-C.
So here's the deal. Network partitions are hopefully rare. Most of the time, your system is running just fine. And CAP says absolutely nothing about the trade-offs you make during these normal peacetime operations. That's the exact gap that PASL-C was designed to fill.
PASL-C looks a little crazy, but the idea is actually super simple. It says, if there's a partition, you have to choose between availability and consistency. That's the CAP theorem right there. But else, when the system is running normally, you face a totally different trade-off, the one between latency and consistency. Do you want to respond instantly for low latency, or do you want to wait for a write to be confirmed across more nodes for higher consistency, which, of course, adds latency?
Okay, let's bring all this theory back down to earth and see how the actual databases and systems we use every day really behave. When you see how they're classified, it makes these concepts totally concrete.
This table shows the different design philosophies perfectly. You've got systems like DynamoDB and Cassandra. They are classified as PA/EL. During a partition, they choose availability. Else, during normal times, they choose low latency. They are built for speed and massive scale. On the other hand, systems like MongoDB and traditional cluster databases are PC/EC. They choose consistency during a partition, and they also choose consistency elsewhere, prioritizing data integrity over everything else.
And that's what it all comes down to. CAP and PASL aren't just academic ideas to memorize for an interview. They represent the fundamental design choices you have to make. Are you building a shopping cart where being available is absolutely king? Or are you building a banking ledger where consistency is completely non-negotiable? Understanding these trade-offs is the first real step to building robust systems that don't fall over. So, which one will you prioritize?